All right, so fundamentally, why do we care about electrochemistry? We care about electrochemistry because we care about building electrochemical devices, right? And so these can range from batteries to fuel cells to different catalysts that use electricity to work to smart windows. Okay, all sorts of different devices um, rely upon electrochemistry. So in an electrochemical device, the easiest thing is to think of a battery, okay? Where you know that you have two sides, right? You have a plus side and a minus side. You look at a battery, you can see that. And these are two half reactions that each transfer electrons. If you think about a battery discharging, that's what we call a galvanic cell. And so in a galvanic cell, when you're getting energy out of the system, okay, it's spontaneous, you're getting energy out of the system, at the cathode, we have the gain of electrons. Okay, that's what the cathode's defined as. Another way of saying gain of electrons in electrochemistry speak is calling that a reduction. Another way of saying that is that the oxidation state decreases. Okay, and from a chemist perspective, it's useful. You know, we think about, well, electrons are negatively charged, given the convention that they're negatively charged. So if we're gaining electrons, it seems like the cathode should be negative. And that's fine in some circles, in chemist circle, to kind of think about it as negative. In the physicists and more the engineering circle, you may know that the flow of electrons, the flow of charge, is defined as positive, okay? And that was the convention that first came into use by Benjamin Franklin. And so because of that, if you look at a battery, the plus side is actually the cathode, okay, which is confusing. But for our purposes as chemists, we are just going to be using kind of the thinking that, hey, cathode is gain of electrons, or gaining negative charge. So we can think of the cathode as becoming more and more negative during reduction. Exact opposite is true for anode, right? We lose electrons. That's going to make it positive. That's an oxidation, and there's going to be an increase in the oxidation state. But because of this funny Benjamin Franklin convention, that is going to be the negative charge. All right, so if you think about kind of a prototypical lithium ion battery, some of the early cathode materials still being used right now to a large extent are cobalt oxide, okay? And so the net reaction during discharge is cobalt oxide plus a lithiated graphite, okay, graphite C6, but this has lithium inside of it, goes to lithium cobalt oxide plus graphite. Remember, graphite is a bunch of sheets, okay? And so we kind of abbreviate this as C6 because each little hexagon of graphite is there as 6 carbon atoms. So we can split this up into half reactions, okay? The first half reaction that's occurring at the cathode is cobalt oxide plus a lithium plus an electron. It's gaining electrons, so therefore it's at the cathode, goes to lithium cobalt oxide. And then the anode, the other half of the reaction, is where the oxidation occurs. So we're losing an electron. Lithiated carbon goes to carbon, or graphite, plus lithium, plus electron. You can see that each one of these reactions is balanced, right? The left side has one cobalt, the right side has one cobalt. And we have a plus charge and a minus charge. Overall, that's going to get you no charge. And on the right side here, we have no charge. So this is balanced. Same thing with this one, right? Overall, we have no charge with the lithiated graphite on the left side. Then we have a plus and a minus charge on the right side. So that's overall neutral. So it's balanced. And so are the number of each atoms. Just like any equation, it's balanced. If you add these two equations up, you're going to get back this original full equation. And then we can assign oxidation states. And so we're not going to go really in depth in this video on assigning oxidation state rules. But you know, oxygen usually has an oxidation state of -2 in compounds. And so since there's two oxygens, that means cobalt is going to be +4. It's an overall neutral species. Lithium, there's only one element there, so it's just +1. That is the charge of the ion, of the cation. And oxygen, again, here is going to be -2. Again, normally in compounds, oxygen is -2. Lithium is +1 because it's an alkali metal in group 1 on the periodic table. And transition metals can be variable. And so we have to figure out what this is. We have two minus 2s, that's a total of minus 4. Then we have a plus 1 that gives us a minus 3, and the whole thing is neutral, so that means cobalt better be plus 3. And so you can see that what happened is oxygen and lithium did not change oxidation numbers. They stayed at minus 2 and plus 1 respectively. But cobalt changed from plus 4 to plus 3. So that means formally, the electron transfer that's occurring is happening on the cobalt center, right? And that cobalt atom is being reduced at the cathode from plus 4 state to plus 3 state. Okay, we can do the same thing on the anode, track the oxidation state. This one's a little bit trickier. Lithium, again, is a alkaline metal, so in ionic form, it's going to be plus 1. Carbon here is actually negative 1/6. And if you think about this, this makes sense because 6 times negative 1/6 is negative 1 plus 1 overall gives you a 0. Carbon here in graphite, that's an element, so it's neutral, so carbon's going to be 0. Lithium, again, plus 1. So what happened? Lithium didn't do anything, but the carbon got oxidized. Its oxidation state increased from negative 1/6 to 0. And that's exactly what happens at the anode. Oxidation occurs. And so what's interesting here is that lithium remained unchanged, right? We call this a lithium ion battery, but really the lithium isn't doing much of the chemistry here. The real interesting chemistry in terms of electron transfer is occurring at the cobalt and at the carbon. But it's called a lithium ion battery because the lithium ions are going back and forth. And so during discharge, we have this reaction that we wrote in the beginning. And you can see here's it discharging. The lithium ions are going to the cobalt oxide cathode to make lithium cobalt oxide. And then when we charge it, we do the exact opposite. The lithium ions are going to the anode, back to make cobalt oxide, formally at least, and put lithium into the graphite. And so, yeah, sometimes these are called like rocking chair batteries. The lithium ions are going back and forth, but they themselves aren't changing chemical speciation. They're always lithium plus, okay? And one thing that is kind of confusing is that during charge, the cathode is actually oxidized. Okay, so that's the opposite of the definitions we introduced in the beginning. And the anode's actually reduced. We still always call the graphite physical structure of that electrode the anode, and we always still call the cathode let's call the cobalt oxide the cathode. But during charge, yeah, the oxidation and reduction processes are being flipped. But this is not a spontaneous reaction, right? The delta G, the change in free energy, is positive. This means it actually takes energy to charge the battery, right? So if you're going to oxidize a cathode, that's not going to be spontaneous. That's going to take energy. All right, so that's just a little bit of an introduction into some of the basic terminologies used in electrochemistry.